Okay, now let's talk about how neural networks are working. So let's assume that we have a neural network in which there is no hidden layer. Hidden layer is not here. We just have a input layers and we just have output layer, as you see there. The one of the simplest neural network. So how then the output layer, the parameter in output layer is calculated? It's simple. All you need to calculate a value in circle here. Value in circle, in this case output parameter in output layer, is based on the summation of these four straight lines. Straight line means you have a four linear equations that is calculated based on the weights. So we just assume that this is weight 1, this is weight 2, this is weight 3, and this is weight 4. So these linear equations are added to produce the number or the neural values in here, and this particularly becomes a output parameters in output layer. So let's calculate output parameters are I1, and we're gonna say this is I1 and I2 and I3 and I4. We have a input parameters name particularly, but it doesn't matter. We just try to carry out I1 and I2, I3, I4 in general. And I1 times W1, so I2 times W2, and I3 times W3, and I4 times W4. This is how we calculate in circle based on the arrows, straight lines towards that particular circle. This is very simple. So that once we know the W weights, then we can calculate the neural values right there. But the problem is we don't know the W1, W2, W3, W4. Therefore, we assume W1 equal 1 and W2, W3, W4 equal 0. What that means is that we don't have all this inferences. The inferences by I2, I3, I4 on the output vanishes because W2, 3, 4 are all zeros. We don't have these inferences. So all the inferences of I1 on output parameters exist. So that the output parameters, we just have a I1, W1, I1, W1. So this will give you output I1, W1. And we're gonna take a look at another example where we have a I3 is equal to 1, I3 is equal to 1, and W1, W2, W4 is 0. Then we have a output value again, now W, I3, W3, where all the inference by W1 to 4 vanishes, as you see here. Okay, I'm gonna say this vanishes, this vanishes, this vanishes. What you have here only W1, W3, so that the inference of I3 on output parameter exists, as you see over there. So this weights determination of weights is very important to see the influence of which input on output parameter exists. So that this W1, W2, W4 is 0 in this case, and how we're gonna determine these weights. These weights are determined basically a process called a training. So training is a process. Training is called a process that determines the weights based on the big data sets. First of all, we have training consists of two steps, two phases. First one is forward calculation, and second is a backpropagations. So in the forward calculation is what you see right there. We just calculate from the input to output all the way. In this case, just one simple step concludes the forward calculations, where you calculate output parameters based on the input parameter and the corresponding weights. And this is a forward calculation results. And the forward calculation results, when you do this, since we don't know the W1 through W4, we assign. Let me just delete all this. We just assign the W1 to W5 randomly. Say W1 we randomly assign 0.7, 0.6, 0.3, 0.5, and this randomly assigned weights is gonna be substituted right there and come up with a output, as long as we have a input parameters also are given. See, so input parameters are given in numbers here, and age in number, Craig in number, retrofit in number, quality in numbers, all that right there. You calculate and come up with a output parameter, output values right there. And then of course your output in the first, at the end of first forward to calculate, it's not gonna be the same as the number that observed based on big data, as long as you're not tremendously lucky or you're not tremendously intuitive. For example, your error occurs that you're gonna calculate and you're gonna subtract your observed value from the calculated value. This is the error. We call this is error functions, or maybe cost function later. So we're going to take a look at in detail later, but I'm going to just explain the brief way of determining weights very briefly right now, so that this error occurs at the end of the first forward calculation. And when you do the back propagations, you calculate based on error, you try to devise weights such that your error can go small, so eventually goes down to zero. Okay, so you go and calculate forward calculation, you go backwards knowing your error value and revise your weight such that your error becomes very small, or eventually it converges to zero. And then you're going to get end of a revised weights at the end of back propagation. Okay, so your back propagation devices weight, let's assume that you revise your weights from 0.7 to 0.65 and 0.6 to 0.5 and 0.3 to 0.25 and 0.5 from 0.5 to 0.55, and for example. Okay, and these are the devised weight from these originally randomly assigned weights, and you're gonna go and do the reverse. This is the first iterations. Okay, and you're gonna do, let me just delete this here, delete here. You're gonna all calculate and repeat the same calculation for second iterations. Second iterations here. Second iterations here. And you're gonna do the forward calculations, and you're gonna do the back propagation in the same way. Then you're gonna devise maybe another weights at the end of second iterations. Okay, then see if you can reduce your error to 0 here again. Okay, error functions, see error functions. So let me see if how many iteration you have to repeat these two phases of calculations, forward calculations, back propagation calculations, until you see your error becomes 0 right there. Maybe to my experience, you may have to repeat 20,000 iterations and 100,000 iterations. If you're a very small system, you probably 5,000, few thousand at least. This is very lengthy process, and each iteration is called epoch. So you will see epoch, the lingo epoch, many times in AI business from now on. And epoch just indicates that one full cycle of calculation, including forward calculations and back propagation, try to revise your ways to try to minimize the error function or cost functions. And how many times do you have to repeat the epochs? And maybe many times. This is very lengthy process, because you start with assigning a weights randomly. Why you pre-assign weights randomly? Because we have no idea about weights. We have no idea about weights. So weight should be randomly assigned any number on the system. You try to do this. Okay, so this is very smart idea if we have good computers, and this is how the most of the AI try to revise your neural networks and determining the correct weights. Okay, and bias same way. This is very powerful method, and with ANNs, and this is what everybody is doing when they are determining weight and bias. And the process determining weight and bias is called a train. Okay, train. Let me just erase this. Train. Okay, so think about it and try to recall this. So now we need the activation function here. This activation functions a function that activates after your response is built up to some threshold value. If your response is less than some threshold value somewhere here, you're ignoring the activation function. Otherwise, which means that your response is built up and greater than the threshold value, then you're going to activate sigma, which makes your neural networks, artificial neural networks, nonlinear. Because of the most of the system, most of the behavior that you see with your engineering equations or your social behaviors or whatever, mostly nonlinear. But as you see over here in neural networks, every relationship is based on linear, which you cannot properly consider non-linear behavior if non-linear behavior exists. And that's how you're going to use a activation function to simulate a non-linear behavior by taking a look at a threshold value. If your build up greater than threshold value, you activate sigma, otherwise ignore sigma. And we're going to take a look at the types of activation function that you use in artificial neural networks, and what kind of activation function is popular and before and now. This is going to be explained again a little bit later. Just wait for a moment. This is where you're going to put a activation function right there. Once your responses build up greater than the threshold value, or the value that you need to consider to decide whether you're going to activate your activation function or not. Okay, here we have a very interesting neural networks here, and this neural networks is very important for us to understand all the neural networks in the future. And I need you to understand this neural network thoroughly with the weights and biases in process called a training I just explained to you, that consisted of two phases: the forward calculations and back propagations, and an epoch, the lingo epoch. The neural networks with the one hidden layer here, one hidden layer. As you see, you have a input layer, you have a one hidden layer, and you have one up layer. We started with the neural networks without hidden layer. Right now we have one hidden layer, still simple, but still very important to understand the general concepts and how to derive how the neural networks is working, is performing its duty, right? So here we have a two input parameters called the x1, x2 here, x1 and x2, and we have a three circles, which means that we need a three neural values, or three nodal values at first hidden layers, and we're going to have one output parameters in output layer. And all this value is located within the circle, which means that either we have received a value from outside, especially for input layer, and the other circles must be calculated, and the number in circle must be calculated to produce the output that we want right there. So and these two layers are seen, so that these two layers are visible layers, but this inside hidden layers, we don't see how the number in the circle is calculated. As you see, the definition of neural networks here is it based on all incoming errors. So this is a invisible calculation. That is why we call the layers in between hidden layers. And